In this lecture, I'll really quickly explain how you can find the energy stored in a capacitor. And this one's kind of fun because you get a result that's counterintuitive. I'll take a look at that before giving away the secret. So the basic idea comes from conservation of energy. And if we have a capacitor that's initially uncharged, so again, initially, let's say what Q naught is equal to 0, and that would be on both sides. Then when we're actually starting to charge it, we start by transferring one piece of charge at a time. So I'll transfer one bit of positive charge, dq, from the negative plate to the positive plate, and in order to do that, I have to do work, dw. And this is where conservation of energy comes in. So if you remember, we would have, say, the initial potential energy, ui, plus the initial kinetic energy, plus the work, is equal to the final potential energy plus the final kinetic energy. And in this case, we're not talking about, or we're not actually changing speeds. So the initial and final kinetic energy are equal to each other, and I'm just setting them to 0. I would also argue that the initial potential energy is 0. But we can rearrange this either way, and we would have that the work is equal to U final minus U initial. And I'm going to leave it at that because then I can call that delta U. So the work is equal to delta U. So this is going way back to previous physics course probably where we talk about conservation of energy. Anyway, you probably remember from chapter 4 that the change in potential energy is equal to Q times delta V. And so that's for a charge Q moving from an initial position to a final position with different potentials. There's an associated change in potential energy. Now, when I'm charging the capacitor, I want to actually not talk about one big charge Q, but talk about delta Q or dQ. So it's a tiny, tiny bit of charge. So du for that tiny charge is going to be equal to dq times delta V. And delta V is the voltage difference that that tiny piece of charge, dq, goes through. Now, we're talking about a capacitor, and we're talking about dq moving across a capacitor. So dq is going to get multiplied by the voltage across the capacitor. Delta V is equal to Vc. Now, for a capacitor, remember Q is equal to C times the voltage across the capacitor, so if I isolate Vc, I just get Q over C, and I can substitute that in. Then the total change in potential energy is just the integral of du from the initial condition to the final condition. And the reason I need to integrate is because the voltage across the capacitor changes as charges are transferred. We don't have a constant delta V. Delta V is different for every tiny piece of dq. So the next step is to substitute in for du, and du is equal to q over c times dq. And then I can pull out the constant 1 over c. So then I'm just integrating q dq from q initial to q final. Q final is the total charge in the capacitor, and q initial is 0 because in terms of the energy stored in the capacitor, you would have 0 energy stored when you have 0 charge on that capacitor. So when I simplify this, then I just get that delta U is equal to Q squared over 2C. And since delta U is really just U final minus U initial, I can now use that fact that U initial was 0. And then what I find is that the potential energy of the capacitor, or the energy stored in the capacitor, is equal to Q squared over 2C. Okay, so that's not surprising. That might be a little odd at first, and you might think, why is Scott getting so interested in this kind of weird result? So the next step is to actually use that Q equals CV expression to rewrite this in terms of other variables, because sometimes you don't have the charge on the capacitor. Maybe you have the voltage, or sometimes you don't have the capacitance. Maybe, you have the voltage. So let's just look at that real quick. So substituting in for Q gives me another expression, U equals 1/2 CV squared. Again, nothing terribly surprising. This is just another handy result that might save you 30 seconds on a test sometime. Okay, the next thing, and this is where it gets more fun. If we isolate C, we have C is equal to Q over V. We get U is equal to Q squared over 2 times Q over V. One of those Q's will cancel out, and then the V comes on the top. And what we basically get is that U is equal to 1/2 Q times V. And this is the strange result, because remember, we definitely used the idea that delta U is equal to Q times delta V. And so if U initial and V initial are both 0, you would expect that U is equal to QV. But what we just proved is that for a capacitor, U is equal to 1/2 of Q times V. The energy stored in the capacitor is 1/2 of the total charge on the capacitor times the voltage across the capacitor. So what's the difference? Well, the first expression is for a charge Q moving from V initial to V final. If we think about the charge moving across the capacitor, the first piece of charge dQ has a delta V of 0. And the last dQ has a delta V of the total voltage or the total potential difference across the capacitor. So for the capacitor, the reason why the energy that's stored is not the same as what we found before for a charge moving from Vi to Vf is because each charge moves across a different potential difference. And it turns out that when you add them all up, the total potential energy stored in the capacitor is 1/2 of Q times V.